I got convinced that at the end of the evaporation of a black hole, something interesting happens quantum gravitationally. And I try to do calculations to actually get some hints about what happens. I don't believe that at the end of the evaporation, just pop, nothing happens, and there is nothing at all. I think that the theory could tell us something more interesting happening.
Now, the local people, Marolf, Shidan, Maldacena, claim this problem is already solved.
I think I disagree with their conclusion. That's my own take. We had a talk this morning about that because they use an assumption, strong holography assumption, which I don't think it's necessary, and I don't see good reasons for buying it.
No, it's not,
this always comes up. It came up during the conference last week. The pitfalls of believing in strong holography and the strong Bekenstein bound.
Who is that? Is that Lee Smolin or not?
That is Lee. Hi, Jim. How you doing?
Hi. How are you doing?
How am I doing? Well, fabulous.
Oh, that's great. I haven't seen, but I haven't been looking either.
We've been looking for you, Jim.
Right.
But
you had Parkinson's disease, as I remember.
Yes, I do have Parkinson's, and not everybody may want to discuss it with us, but I'm doing well.
Okay, good. Well, we're doing all right here in Santa Barbara. I haven't been out of the house for about 2 years, but aside from that.
Let me say that my neurologists say I should have a test for when there begins to be some cognitive issues. So I say if I ever start espousing the many worlds interpretation, they should check me out.
Yes, that would be good.
It would be great to talk sometime.
All right, so there seems to be enough participants. We're having a small issue here that for some reason I don't seem to have recording rights, which is a shame. So Pierre is going to record the screen on his computer and I will record the audio. But in case there is somebody in the...
Do I have to give you the recording rights or something?
I haven't actually asked you, yes. Are you okay with recording, James? We can record it and then we can ask you about it. But if you would prefer to not put it afterwards up, actually, that would be convenient.
No, I'd be happy to have it recorded, right? Because everything will be up on YouTube and there should be the talk as well as the visual.
Yes.
Or you are doing that. Everybody else is doing it. I just guessed it.
Yeah, yes.
Put the talks on YouTube?
Yes, we do. We have a YouTube channel where all the talks are later available. So I wanted to say that if one of our friends here has the possibility to record screen.
So, who is the host?
Yes. I am, and Jim is co-host. No, but this is some issue because I changed affiliation. I don't know, probably in the settings. I had changed it last time for the seminar that Bob Cook and was working, but apparently I have to do it every time. And we would have to now log out.
Maybe, so two things, Mario. So one thing is use your official Vienna email to log in. And the other thing is check the security.
I'm logged in from Vienna, but I tried to change it from the back end, but right now we would have to all log out and log in again, I think. So it's okay. Pierre is recording the screen and I'm recording the audio.
Can't you give permission to other participants to record, and then one of
it's
us
not
will record?
allowing recording in the session at all.
At all?
Mm.
Okay.
But
What if you make somebody else host, somebody who has a Zoom subscription?
No,
Could
this
they record? No.
it has to do with the link. The link is
The
created
link,
through-
right.
That's okay. No, I was saying if you have any other, the screen recording softwares, in case somebody has it, please record it, and then you can send me a link. But for now, let's just hope Pierre's computer will manage to do it, and I will have anyway the audio that I could synchronize the slides. James, I'm sorry for this technical issue, but we do look very forward to your talk and discussing.
Mhm.
Thank you very much for accepting the invitation. We are a bit starting a bit late, so if you would like, I can remind you when it's 30 minutes, but we will not interrupt you. You can go on if you still have things to say.
I've aimed it for 30 minutes, and so I should be good.
Great.
I'm more interested in the questions in the discussion than I am in my talk.
Great. So if you're ready, you can start.
Shall I begin?
Yes.
Okay. Oops. I can't move I can't change my slides suddenly.
That happens. Try different kinds of buttons.
Try clicking on the slides first, maybe.
Oh, there we go.
All right.
Okay. At the top of the website, I noticed, which is pointed out to me by Bob Griffiths, right? You have a series of questions, right? One of them was, what do we feel if we're living in a superposition of states? When I saw that, I realized I'd written a paper a long time ago called Living in a Superposition, and you can find it on archive. The exact number was down on the bottom of the page, but it seems to have been cropped off. And so I want to talk about that today. What do we feel if we're living in a superposition? Now, like all stories about quantum mechanics, we start with the two-slit experiment. Here it is, an electron gun. Here, screen with slits U and L. The electron goes from two regions, and it creates this interference patterns. This picture, by the way, assumes a classical background spacetime, which in a quantum mechanics of cosmology is something that we should derive rather than assume, but I'll get back to that. We have to click on the slide, I guess, to start. I've got this now. So imagine that instead of an electron, you had an ant going through the two-slit experiment. What do you think that the ant would feel if there's another path it might have been taking? I think the answer is no. I should say what I mean by feel. By feel, I don't mean like, I feel like voting for Trump. I mean some physical sensation, right? That is an interaction with something else, right? Which I feel, right? Heat, cold, pressure, something like that. And so in this simple experiment, there isn't anything else. So the ant doesn't feel anything. Experiment has greatly increased the size of physical systems that can be put in quantum superpositions of macroscopically distinct states. Let's see, I can't move this. Can you read this? I'll just read it, I guess. Somehow the pieces on the side of the screen are blocking the thing.
We can see the screen well.
Well, I can see that you can see the whole screen.
Yes.
Okay, so there's not, I see, so the images of who's listening are blocking it, but that's all right. I don't need to see all those myself. A lot of those experiments were done by Anton Zeilinger and his students, successors. A picture of this is down on the right. I put that there because I hoped that he would win the Nobel Prize just a few days ago. And I could say that I anticipated that. Here's some of the data about large biological systems showing evidence for being in a superposition. Here's a particular molecule, this is experiments done by Lisa Hackemer et al. And she's now in Nottingham, I think, still working. Large biological molecules can be put in superpositions of states. Here's more evidence from work by Gerlich et al. In Nature Communications of organic molecules, that's these things, right, being put in superpositions, and here's the characteristic interference pattern. So these are done by Talbot-Lau interferometers. It's the exact analog of having the two-slit experiment, but with more slits for the molecules to go through and interfere. We could even imagine, as this thing shows, putting a cat going through a two-slit experiment. We're not doing that yet, and we would be arrested probably if we did. It also, in principle and calculation, would give an interference pattern. So there are plenty of superpositions, but what the thesis of this is we won't see, in some sense, or feel in some sense, superpositions that we're a part of. A very familiar example is the Schrodinger's cat example. In the usual story about the Schrodinger's cat, the cat is in a superposition of two branch wave functions, one in which after 20 minutes it'll be alive because the Geiger counter has gone off and the flask of cyanide has been broken, and the other, in for 20 minutes, it will be, I'm sorry, I got them backwards, one of which they'll be dead and the other which will be alive. But the cat doesn't feel the superposition. The thing is, the setup is so simple. There's no interaction of the cat with the room and no mechanism by which it could tell ahead of time, right, that it is in a superposition of those possible states. It just has to calculate it. And that's true with all observers. Right? Observers are outside the system in general, when we're talking about. So we ourselves could go through a two-slit experiment, right, and be put in a superposition of state in that paper, which I alluded to, that's discussed in detail. This has all to do with quantum mechanics, right? And I want to talk about the quantum mechanics now of other sources of superpositions of state and cosmology. We start with the idea, which seems reasonable, that if the universe is a quantum mechanical system, that is, if quantum mechanics applies to the universe, then it must have a state if it's a quantum mechanical system. What is that state? it's not something we discover by experiment. After all, there's only one universe. We don't have a chance of doing statistics on a large number of them. So it has to be something that's part of the posited as part of the fundamental theory of the universe, along with the theory of dynamics. And what is that theory of the quantum state is the objective of the field that's called quantum cosmology. So we arrive at a system where the fundamental theory in physics consists of two parts: a theory of the Hamiltonian, if you like, or the dynamics, which mostly tells us about regularities of the universe in time, and a theory of the universe's quantum state, which tells us mostly about regularities that emerge in space. For example, homogeneity and isotropy on scales above, say, 100 megaparsecs. So there's an unfinished task of unification here, which in some sense is solved by the no boundary wave function, but let's not go into that. This is just a list I thought it would be useful of what those two, the dynamics and the state, say about are important for. The dynamics, of course, is important for classical dynamics and for laboratory experiment, for example, stuff carried in it. The state is responsible for many other features of the universe, which are not experiments. The existence of classical space-time, the fact that those classical spacetimes are homogeneous and isotropic and inflate, but they have fluctuations in the ground state, which we see in the CMB and the large-scale distribution of the galaxies, hours of time in the universe. Here it is again, CMB isolated system, and the topology of space-time, if that's allowed to vary maybe the number of large and small dimensions. But that means, right, if you have a theory of possible histories of the universe, that from emerging from that state, that you're already in a superposition of the whole universe of states. How do you feel? I'll describe this a little more fully using a model here. Imagine that we constructed a large box with flat space-time inside, say 20,000 megaparsecs on the side. That's everything is inside this box. Stars, galaxies, you, me, us. And there are no observers on the outside looking at it. So we have to deal with it, just like we had no observers outside the real universe. The theoretical inputs to such a computation to such a theory are the theory of dynamics and the quantum state, which I've already talked about. Of course, for the theory of the state, we're going to take the no boundary wave function of the universe by Hawking and me, but for computations. But there are many more possibilities for what that might be. Now, who are we in the universe when we talk about, as observers of the universe, we're physical systems within it, along with our apparatus. We're not outside looking at it. You have to get used to that. You can't talk about observations of the universe. You can talk about observations that are made inside the universe. And here is an attempt at a lot of equations being summarized in a very simple way. Different histories of what happens in the universe correspond to branch wave functions and the wave functions of the universe. So a time history of the universe is a sequence of events at a series of times. That's just a definition. Individual histories can be represented by branch states. The branch states sum up to the whole wave function of the universe. Thus, inevitably in cosmology, we're already living in a superposition of the states of the branch states of what could happen in the future. Thus, generically, it's not a special situation that we're in a superposition of states. We can analyze this. I didn't have enough time to fix this slide. In the context, we have a formulation of quantum mechanics that's good enough to deal with all that. It's called Coherent Histories Quantum Mechanics. It's the work of many people. It's not anything new. It's about 40 or 50 years old, right, from the time of Griffiths. Here are some of the major figures. Bob Griffiths, and there's about as much time to Griffiths discovering this as there from Heisenberg as it was from Heisenberg from the formation of quantum mechanics. This is Murray Gell-Mann. And it's not something special. It's already in, if you read the lamentably late Steven Weinberg's lectures on quantum mechanics, there's a whole set of chapters on this. It's the way to do quantum mechanics for the universe. Decoherence. To predict probabilities that are consistent with the rules of probability theory, that is, additive and so forth, the branch wave functions have to be orthogonal. That is, two different, the quantum, or put it a different way, quantum interference, right, has to vanish in order to have consistent probabilities. You can't just square the wave function, they have to satisfy a condition. And here's the basic formula of the whole thing. The branch wave functions are orthogonal, and the value of the branch functions gives you the probability of whatever the history is. There are a lot of misconceptions about this. We're not somehow smeared out over the branches of the wave functions. I wouldn't even know what that means to say that it's smeared out. The branch wave functions are mutually orthogonal, as we've just seen. That's decoherence. That means one happens and the others don't happen. But there's only a probability. It's just like having a die. There's 6 things that might happen, but only one happens, and there's a probability that one comes up.
James?
People can't communicate with any of the branches because there's no mechanism for perception. It's just part of the theory.
James?
Yeah?
If you don't mind being interrupted, there is Liz Mollin that has a question.
Yes, Jim, one thing that's been obscure to me about this kind of formulation is what the role of causality is. If I agree that we're always inside the universe, making observations or seeing the universe, but shouldn't we distinguish the universe to our past and our relation to that from the universe to the future?
I'm glad you asked that question. It's too bad there isn't another seminar, right? So we treat both the future and the past symmetrically from the formalism. That is, we have at any one given point, we have a certain amount of data. Right? To predict the future, we take histories that start from that time and go to the future, make sure they're decoherent, and calculate the probabilities. To retrodict what happened in the past, we take histories that go the other way, backward in time. This assumes there's a kind of local space-time, which I'll get back to, but assuming that, you then retrodict, and all the retrodictions are also physically equivalent, and there are many of them. So just like there are many possible futures, there are many possible pasts with probabilities. So we have, read in a history book that Julius Caesar invaded Britain in 55 BC. There's only a probability that actually happened. A lot of things could happen. It might be wrong. It didn't invade. The ink might have jumped off the page quantum mechanically and rearranged itself in 58 BC. All sorts of things can happen, which we can calculate. So we can calculate both the future and the past from one wave function, if you like. But at any rate, we repeat, living in a superposition therefore seems generic. If you think that your past history has any consequence from quantum events, for example, evolution, there was that cosmic ray that came through your father and changed the genes a little bit and resulted in their change in your personality and so forth. So right now you're living in a superposition of all those possibilities. How does it feel? That's the end of my talk, really. Superpositions are generic. Almost every isolated system in the universe is a superposition of branch wave vectors describing its possible quantum evolution into the future, and we should just get used to it. To conclude, I'm very interested in the questions, and I have some suggestions for them. Can you see that? It's sort of a little hard.
We can see, yes.
Yeah, only I can't see, but I don't need to see. Are there other wave functions other than the no boundary wave function? The future is probabilistic. Is the past permanent, unchangeable, or is it also probabilistic? Well, I already answered that. What is the evolution of complexity in the universe? One of the reasons we have to have probabilities, distributed probabilities, is to deal with the evolution of complexity. Our universe, and even in a classical description, is very complex, right? We can't have one wave function giving one history because all that complexity would have to be encoded in the wave function, which would make it not manageable, discoverable, or really useful, consistent with the general ideas in physics. Decoherent histories might be the only possible formulation. And then you can ask, how do we calculate where physical systems within the universe? Suppose there's an exact copy of Lee. At least to the coarse graining that we would like. Not perfect. If we took one proton off Lee's forehead, it would still be Lee. Suppose there's a duplicate of that elsewhere in the universe. After all, in a large universe, the probability for that is 1. So how do we deal with that? How do we calculate in that? Well, I have an answer to that too, but I don't think it's relevant here. Answering these questions will be full employment. Thank you very much.
Thank you.
How do I do on time? Maybe it was only 10 minutes.
9 minutes ahead of time. So anyone that
so I was right up to 50 minutes.
Yes. So
perfect. That's as good as I get.
So anyone that wanted to ask a question to James, I think this is your opportunity.
By the way, my mother called me James, as in, James, your shoes are untied. Everybody else calls me Jim.
Okay, I will from now on. So, Jim, we have already Carlo raising a hand, and I think after Carlo will be Lee. And I encourage everybody else to ask questions in the chat or raise a hand in the chat. Carlo?
Thank you, Marius. Thank you, Jim. I'm tempted to go like your mother and say James at this point, but I'll stay with Jim. It's just to break the ice and open the discussion. This is a beautiful discussion. So I want to make a couple of comments about what you said. First of all, I think there's absolutely nothing I disagree in everything you said. So I think it's the main point is convincing. It's or at least I find convincing, and is wise. So the main message is, how do we feel by being in a superposition? Well, we feel exactly like the way we're feeling now, whatever feeling means. And the coherent formulation histories, the formulation of quantum mechanics and interpretation of quantum mechanics it's a beautiful one, in my opinion. I think it's not the only one possible, available. I think there are alternative possible ways of viewing quantum mechanics, which are also consistent. And I think that in any one of these, the conclusion to the question, how do we feel if we're in a superposition, should be the same.
Exactly.
That's my understanding of the situation. Now, specifically, the way you have presented the story in a very nice and compact way, you have a Hamiltonian and a state. And the comment I want to make.
I mean the theory of dynamics.
Yeah,
so
sure. I mean, I know I know the more refined formulation of the story, because I know your papers. But you have these two ingredients. And one remark I want to make is that the role that the Hamiltonian or the theory of dynamics play here, it's very similar to the role of the state, or more precisely, the role of your state is very similar to the role that the dynamic, the H, plays, because your state is very far away from the state, say, of many world interpretation, and perhaps even from the state of pilot wave. So your state is not the stuff of the world which is out there, fixed, out of which we have to derive something. It's part of the formalism that that allows us to compute probabilities. And what the theory is about is not really about the state. It's about what you call the individual histories. These are the things that describe the world, to which, thanks to the state, we can compute their probabilities. Now, furthermore, this is the first observation about your state. Furthermore, that state, is not the state that is used in a laboratory.
No.
Because as you said, when you so if you know something that has happened and you want to compute the future, or if you know something that happened and you want to compute the past, I mean, the probability distribution of the evolution in the future, the probability distribution of evolution in the past, you start from some local information you have, and you have a state that it's about the local information, the specific information you have, which is much more similar to the relative state of Everett, or to just a little branch, if you want, a little piece of this large state, but it's not the full state. So the state we're talking about when we are in a quantum mechanical situation, it's generally a little grandchild of the big state you're writing out there, which is the overall one. And in a sense, that is the one we know, because the only thing we can say about the big psi is from the individual, the specific data we have about the world, unless, of course, we go to the no boundary or similar. I mean, no boundary is probably the most beautiful of all proposal from the overall state, from which, however, realistically, we're not going to compute the probability for something happen tomorrow morning in my laboratory, unless I insert the fact that I already know something about that. So these are some comments to break the ice. So I want to express my agreement, but also the points in which I would say a few things slightly different. I'm curious to know how would you react to these comments.
Well, you've just raised a lot of issues, right? And I didn't record all of them, about the predictive property of the state. In principle, for example, if you have the quantum state of the universe and everything, you can calculate the probability that the New York stock market will go up tomorrow or down, right? Those are alternatives in the future. I'm pretty sure that the probabilities you would get are 50-50 from this data. Bad luck, right? That doesn't tell you anything. That's one thing.
Otherwise, you will be richer already.
What?
Otherwise, you will already be much more rich.
Well, that's what Gelman used to say. If you know the function of the universe, why aren't you rich? Well, that's a whole other story working with somebody like that. The other thing I want to mention is our universe has classical spacetime. In that classical spacetime, we can formulate the quantum mechanics of measurement situations, which are regular situations. We can formulate hydrodynamics. We've devoted a lot of effort to showing approximately how those things emerge from the wave function of the universe in a simple theory of the dynamics. Classical space-time, not everywhere, but in patches. Then the usual rules, for example, for hydrodynamics and Copenhagen quantum mechanics, which assumes classical space-time, right? When you have actual measurement situations. In other words, we calculate all those things. So I agree with you. Just stating the wave function of the universe doesn't tell you very much of anything. You have to do some work. And I think that was what you're trying to say.
Lee, feel free to jump in.
Okay. Let me jump in at the point, Jim, where you said that the probability for another me somewhere else in the universe, I presume, is 1.
The probability for what I just missed.
For another, I was very flattered. The probability for another me.
Oh, Lee, right.
Was 1. And I presume the same is true for you and everybody else. So this is the point where there are many things, and we've been having this wonderful conversation for decades. And there are many things about which we agree. We agree that the universe is described from the inside.
Right.
But I believe it's described from the inside in such a way, and in fact, this is one of my principles, that the probability of another observer or another event observing what comes from their past to be the same is 0. And I apologize for the dawn.
0?
0, yes, 0. My principle is that no two events have the same information coming in from their backward light cone.
What do you mean information?
Good. So my conception, and I've been working on this with a number of people, is that what the observables are, or the beables in quantum cosmology, are connected with events. And events have classically backward light cones. And classically, we know what we mean by saying that information comes up from the causal past of an event to that event. And in some sense helps the causal.
You're already assuming space-time.
No, I'm assuming a property of space-time, which is that the world is made of events. And the world is, the beables are properties of the histories of those events.
Okay, I don't understand that, but that's all right. We don't.
Okay, and one of the first principles is that it's a dynamical principle, that every two such backward views. I call what an observer receives from their causal past that distinguishes it from other causal pasts, the view of that event. And one of the principles that I believe is interesting to build on is that the probability that any two of those views of the past are identical is 0. So it's interesting to me that we differ exactly there, but so I want.
A difference is, I think you're assuming classical spacetime to give a notion of the future and the past.
No, I'm assuming, in fact, I don't have a notion of the past. The notion I have is view of the past by an event at the present. So my quantum universe has no past and no future. It does have a present, and the present is made up of events, and those events have properties, which are what they observe of their, quote, past, but that past does not exist anymore. Just like all that exists now of the Roman Empire are the books and the records and libraries and paintings and so forth. All that exists of any of our past is the records at our present moment. And the universe consists of the collection of those present moments. And they're all different.
Oh, no, I read your book, right?
Yes, but you didn't read the next one. But thank you for reading it.
I didn't realize there was a next one.
No, thank you. Yes,
Yeah.
but that's the basic idea.
Okay, I understand what he's doing. I'm not doing that, right? From reading his stuff, right? I don't think we should debate that, Lee. I don't think we should debate this here. The conclusion, I think, for most people is there are different points of view, right? They should pay attention to you.
No, okay, great. Great. Go ahead.
Actually, I mean, yeah, we should go on to other questions, but if you do have a comment on this, whether you are proponent of the block universe and somehow the more objective existence of the past and the future or not, feel free to comment.
Well, I have a lot to say about that. I wrote a whole paper on the past, present, and future. It's called The Physics of Now, okay, which I'd be pleased to supply. And I've organized myself, right, at the Santa Fe Institute, workshops on this subject or conferences on this subject where all this stuff was discussed. Could we focus a little more? I think there are multiple pasts as a key thing. Maybe that would set things up. Because just like in the future, you have different histories in the future with probabilities. So also in the past, given present data, you have different stories about the past with different probabilities.
Would you agree with what Heisenberg said, which is that the quantum description applies to the future, and when we talk about the past, things definite occurred or didn't occur, and therefore the quantum wave function description does not apply?
Is it what?
Does not apply. Because Heisenberg thought there was a fundamental difference between the treatment of the future and the past in quantum physics.
Do you have a reference to that?
I certainly do. I'll send it.
Will you send it to me?
I will be happy to.
I don't think so. What can I say? I think Heisenberg was wrong.
Okay.
But
just for the record, so do I. If he said so, I think he was wrong.
So at any rate, send it to me, please, because I've looked for it and I didn't find it.
Mm-hmm.
Also, I think I've asked you for it again, and you a long time ago, you supplied it, but now I've forgotten it. Just wait, young man.
We could come back to this. I will open the discussion to other participants that have been waiting to ask a question. Matthew Fox, would you like to ask your question?
I guess I'm struggling. This was very redolent to me, at least, of Carol and Singh's Mad Dog Everettianism. And I'm trying to understand what is the true difference between this decoherent histories approach and Everett, just in general.
Well, usually, I mean, I just read a big paper by, let's see, what's his name? Escaping me, senior moment here, right? On many worlds. And one of the things they claim is decoherent histories is a variant of many worlds. I'm not going to get into them. There are many histories, right?
Are you choosing then just a particular choice of the universal wave function?
No, I think it would be true for any choice. For example, there are many different wave functions in the universe. Biankins, for example, I think it'd be the same there.
Okay, and then I guess my other question was, is there a requirement that that universal wave function be a pure state, or does it matter if it's mixed? Or does that even make sense to say that it's mixed?
Well, you could have it mixed, right? Usually in mixed, I think of mixed, but I've been told I'm just completely wrong on this. I usually think of a density matrix as probabilities, right? For which state occurs in an ensemble of possible states.
Mm-hmm. And then not to keep asking questions, but just one more.
But formally, you could do the whole thing with rho instead of psi.
Yeah. I know people at UCSB like Steve Giddings worry about the factorization of space-time or of your Hilbert space when you're trying to do this really bare bones approach to quantum mechanics and to the quantum wave function. How is that, is that an additional assumption that you're making when you're trying to talk about the universal wave function, how that Hilbert space factorizes?
What is the factorization in Hilbert space? I mean, it mean into tensor products?
Yeah. But it's not that yet. Depending on how you factorize your Hilbert space, it engenders different properties of your wave function.
Okay, one wave function, it's either equal to some tensor products or it's not. I don't know what the question is.
I guess there are requirements. I know Carol makes arguments for why the Hilbert space should be, quote, locally finite dimensional, for instance. And there are just assumptions on your Hilbert space in order to get more structure just out of this bare bones Hilbert space structure that you have.
I don't understand that either, right? Who is it, by the way?
Carol, Sean Carroll.
Oh, Sean Carroll. Yes. Okay. Well, I like Sean, but I wouldn't like this. Do you believe that the wave function in this room is factorizable or not factorizable?
I kind of agree with his statement that it's locally finite dimensional, just by arguments that you can only have so much information packed in a region of space-time, so you expect the Hilbert space to not be...
Yeah, but he's working from he's assuming some classical space-time just to make those stations. I'm trying to treat space-time quantum mechanically. So there isn't any pre-described notion of local.
I think he's trying to define local in space-time. I'd have to think about it more, but yeah.
But we have another question, right? I mean, the question is really to Sean. So if the question is, do I agree with Sean? In most cases, I do agree with Sean, and I followed his career with interest when I gave him his first postdoc. So I pay attention to what he says, but I don't always agree with it, and that's the case here.
I think Carlo wanted to comment on what you just discussed.
Just one line. Sean Carroll MacDog Everettianism, it's completely different than Jim consistent interest interpretation, because Sean assumes that from psi in H period, you can derive all the rest. Well, Jim assumed that there is a set of individual histories, which is part of the theory.
Mhm.
So there is some much more structure which is given in the Coherent histories formalism than in what Sean would like to do. And I think Jim is right and Sean is wrong, if you want my opinion. But that's a distinction. If you only have a Hilbert space and a Hamiltonian, you don't get the world out of it. You need more.
I see. Thank you.
Okay, thank you. Ikislam, would you like to ask you a question?
Yes, thank you, Marius. So it was a very interesting talk. So I read your paper before, Jim. I also read Lee Smoling's book, so that's very interesting to listen to the viewpoints and see how they fit together. For the purpose of the question I wanted to ask, I'd like to come back to that cat. I mean, I love cats, and thinking about how the cat feels is very interesting. And let's assume the cat is called Descartes, right? And so that cat might think, okay, I think, therefore I decohered, right? Because if you think these are all classical states that your nerves somehow have classical bits, at least this is our experience. So I think, therefore I decohered. So decoherence, that's also related to Matthew's question indirectly, but I think of that of simply, in configuration space, the supports no longer overlap, and then the number of dimensions is so high that they will never ever meet again, right? So this is how you end up in a mixed state. But basically, I think, therefore I decohered. If you exist, and your thoughts must have decohered. So if you ask the question, what do I feel when I'm on the path, when I'm crossing these two slits? If I'm aware of being in one of the two slits, then it means I decohered, but then it should mean that there is no interference, right? So if you take the converse of that, it means that if there is an interference pattern, doesn't it imply that I did not decohere, and then part of me went through the upper slit and the other one through the lower one? What I mean with that is the only things that decohere, these beables, these macroscopically observable things, we can only think of what actually is a beable. So the deeper question here is, does it make sense to ask how the cat feels without actually measuring the actual slits? And if you continue the reasoning, then that's directly related to Lee Smoling's observation that your memory of the past is a record of the past, but it's not the same thing as the past. So if you're thinking of, does the cat remember whether she went up or down through the up or down slit? If you assume that the memory of the past is the same thing as the past, then it means that even remembering having been through a slit would imply that there is no interference. It's just my naive reasoning when I think about that, and I would be curious to hear how your thoughts map to what I've just said. Like how does your reasoning plug into this? I think, therefore I decohered way of looking at things for the cat.
I think, therefore I decohere. What an opinion about that. I imagine that you're talking about something that goes on in the brain, and it's very likely that the structure of the brain at the level we're probably talking about has decohered from interactions with photons and so forth, right? I don't know how to calculate that, but it's very plausible, so it's already decohered. But I don't know, I think, therefore I decohere. Thinking is some mental process, and I think, let's take an example. What if we have a nice computer isn't it thinking? Oh, well, I think yes. And the parts of the computer will decohere in very standard ways. So I think I'm agreeing with you, although I don't like the way it's stated.
Okay, on the package, on the formulation.
Beg pardon?
You disagree on the formulation, but not on what's below.
What formulation? I missed it.
So basically, I think if I just summarize what I'm saying, I'm just thinking of, yeah.
If you could maybe summarize the.
Yes, that's what I was about to do.
Yeah.
I'm basically just asking if asking the question, what does the cat feel when it goes through the slits, as you suggest, isn't that precisely making a measurement and modifying the system itself? Meaning that asking the question in itself is a perturbation to the system.
In Copenhagen quantum mechanics, right, you make a measurement and then it's recorded somehow. And recording means that there's a rough sense, that there's a record that is accessible to many people or ants or something like that. The same is true, presumably, with the cat going through the two slits. It will have a record of what it felt like going through the two slits. Whether it noticed the gas, for example, that was doing the decohering or other things. So it's just a complicated physical situation, and it can be analyzed in this way. I don't disagree with you about memories of cats, but it's not fundamental to what I've been trying to say, I believe.
Okay, I'll take the time to digest that based on that food for thought. Thank you.
Thank you, Gislan. Marco, you do not want to ask your question more?
Let's see who is talking.
I do have to ask the question. I don't know. The hand was lowered automatically. I didn't lower the hand. But
maybe I did it by mistake. I'm sorry.
I don't need to see that. Right?
I wanted to ask a question that was that is related to this discussion about what the cat feels. I think that
sorry to interrupt, Marco. James, would you like to stop sharing the slides so we can see each other? Maybe that's better.
Maybe better. So
I can do it on my side.
Oh, yeah, good.
Just 1 second. All right. Yeah.
And Marco, can you speak closer to the microphone, maybe?
Me?
Can you hear me better?
This better?
Yeah. Okay.
I don't know why it's so faint. I don't think it's me. I don't think it's on my end.
No, maybe you can speak louder, Marco, or raise the volume.
I'm sounding. Oh, well, let's see. Maybe what if I turn my volume up a little bit? Well, it's already up. Does that help?
Oh, Jim, you're fine. Jim, you're fine. It's Marco that was low volume.
Let me try to fix that. Just a second. Maybe you can let the next question go on while I try to fix this. Okay?
Can I just make a little statement? There are a lot of complex systems in the world that obey the laws of physics and their activities and so forth.
Okay, can you hear me better now?
What? Yes, can you hear me?
Yes,
Nobody...
to both of you.
Oh, I see Lee.
Yes,
He's
I'm always
blown up to some enormous size on my screen. At any rate, let me just finish this. There are a lot of complex systems, right, that can be understood by classical mechanics, by Copenhagen quantum mechanics, by theories of an overwhelming theory of the wave function of the universe and its dynamics as special cases. The problem is to derive those. So, for example, Murray and I took that and derived the Navier-Stokes equations from a quantum set of histories that dealt with the usual variables of the Navier-Stokes equations, that is densities of momentum, so forth. So cats presumably also can do that, but I don't know how to do that, or what cats feel. I have enough trouble figuring out how I feel.
Can you hear me now?
Can you? I can hear you. Yes. Can you hear me?
Yes.
Hear you both. Yes.
Okay, good. So my question is about this thing, what the cat feels. I think that we should focus. There are two parts to that question. There is a part that I find relevant, and there is the part that I find not relevant. So,
are you at the Schrodinger cat experiment, or just some other cat experiment?
No, I'm referring to the idea, to the experiment where you push a cat through a double slit, and then yeah. So and the question is, what does the cat feel or perceive or something like that during the flight? So if there is decoherence between the two wave functions, then of course we all agree that the cat will feel the same way as it feels, as we all feel in a classical kind of sense. The actual relevant question is, what happens when the two branches of the wave functions are not orthogonal, right? So there is no decoherence. So when we actually see the cat interfere with itself on the screen, whatever that may mean. So after the cat interferes with itself, it will have to have forgotten which slit it traveled through, right? Because otherwise there would be a record of the path of the trajectory and so on. But during the flight, before the actual cat reaches the screen, the question, what does it feel during the flight in a non-orthogonal superposition of two different trajectories? That is the question that can be non-trivial, that can be interesting for me. So do you have any comment on I mean, that I think that people are using decoherence to sidestep this question, but it is not something, I mean, it is not something that is easy to do in a laboratory, obviously, but theoretically, at least from the point of view of quantum mechanics, it is something that can happen. It is doable. So the question is, what would a person or a cat or whoever perceive during the flight in a double slit experiment before it interferes with itself again? So do you have any comment on that? I mean, that is the thing that I believe is the most interesting part of this whole thing, right?
Well, there's some comments on that in this paper, but it's a question of, I don't think I have a theory of me. I should bring my cat in so you can see. I'm pretty sure the cat doesn't have a theory of what's going on. If it's a physical system, in principle, we can calculate it. There are a lot of stuff like you're asking, like what does the cats feel? That's already a problem expressing that merely in physical terms, which is all I have. So if I took my brain apart, would I know how I feel in terms of the distribution of the matter in the brain? There are a few cases like that, like we know, for example, that if you press on the hypothalamus, right, then people experience vivid memories of the past. That's the Wilder-Penfield, right? And which are not true, right? So I'm not sure. So I don't think anything I have in quantum mechanics says anything about that. Right? In principle, yes. So if you go in the stock market and make a lot of money, you can establish a foundation for answering this question. Then I will work on it. Otherwise, I'm trying to just deal with things that I think will have an outcome and not so complex that I can't possibly understand or model it, as in this case.
Well, the thing about I mean, okay, I agree with you that what does a cat feel, or anybody of us would feel, in principle, is not a physically well-defined question. But one can replace that by a question that is more tangible, in a sense, that is the question of uniqueness of outcomes, uniqueness of perception, right? So in my if I am traveling through a double slit, will I perceive only one reality, in a sense, or not? I mean, the question is, do I observe a unique universe around me while I'm traveling in a superposition? I mean, that is I agree that it is still an ill-defined question. But I think that with maybe a little bit of effort, it can be made more rigorous than it is now. So it's
Please get the answer. I provided the formalism.
okay.
I don't think it's going to be easy.
Oh, of course not.
So do it. Find out.
Can I just cut into Q, and because this whole question about how the cat feels, I think that we can make it more operational so that all of these arguments become a little bit simpler. I know that Gia Ding was in the queue before me, so I'm cutting in. I hope nobody minds.
Actually, Deepak, please go ahead. Marco asked my question. That's why I lowered my hand.
Okay. No, so when we say that somebody feels something, right? I mean, if I ask Ding, how are you feeling, right? Well, right, Ding gives me an answer, right? And
I feel great.
And let's let's say like Ding goes on a journey somewhere, and I ask him to record his feelings. Well, he'll carry a notebook with him, and at periodic intervals of time, note down how he felt, right? So I mean, from an operational perspective, I think we can say that this cat, or whatever this system is, right, is carrying a recorder with it, right? Which can record whatever, some data. And then
getting a coffee at Starbucks. I was in the parking lot, and there were two men there talking to each other. And one of them said to the other, "Well, how are you feeling?" And the other one said, "If I knew, I would tell you."
No, but that's also like information, right? I mean, regardless of any kind of philosophical context of that sentence itself, those words themselves constitute information, right? And the person uttering that statement is making a record by the act of speaking those words, right?
I will do better, right, answering questions that have to do with the real physical world and not cats, not feeling, not the brain, about which I know practically nothing.
No, so that's what I'm saying, that one doesn't have to talk about cats or brains. I'm just trying to put the whole double slit experiment, just frame that experiment in a way that one can ask meaningful questions about it.
Deepak interest, is there a way to formulate this question without using living things?
That's exactly what I'm trying to do.
Let's imagine a macroscopic device that is recording.
Right. So one doesn't need to like ascribe any notion of life to the system in question, right? I mean, you could say that it's a sufficiently complex system, which for all purposes like satisfies the attributes of life, but it has a recording device, it has a diary, right? And we send this system with a diary towards the slits, and we ask we tell that system to record whatever we mean by feeling, right? So let's say, what do we mean by feelings? Well,
oh, by the way, I mean, the feeling is a problem, right?
No, it's not really, because see, we are making it more complicated because we are like making it anthropic. So instead of that, we just think of the system as having a set of states and a tape, right? Like a Turing machine. And it just records whatever is the next output of that Turing machine, right? And that is what, let's say, we say that is the feeling of the system, right?
Oh, I see.
If you
want to say anything recording is a feeling? So I'm writing down a little book here, right? Question, that's not a feeling.
Well, no.
Let's say you throw a video camera that's turned on. I mean, if you imagine a cat, you might as well throw a camera, right? So
sure.
It's turned on, it goes through the two slits, it comes back. What's the problem?
Exactly. So yeah, you can ask that also. Put a camera with the cat.
Right. Well, what is the problem?
No. So that's one way to frame is that when you get to the screen, right? What is the state? What is the information that is recorded in that camera?
When you get to the screen, the position of the electron up to it's of course entangled with other atoms and molecules, but it's roughly a position, and the photographic plate goes dark there because of interaction.
No. I'm talking about the video camera, which is being carried by the cat or the system.
Sorry, what video camera? Did you say video camera?
Well, I was just following up on Mario's suggestion. Anything, it doesn't have to be a video camera. It's just a diary, right? And whoever that system, whatever that system is, we instruct that system that, look, just periodically record, quote unquote, your feelings in this diary, right? And then we send that system along with the diary towards our double slit.
Okay, here's the system. The system is one electron in the two-slit experiment, and it hits the screen, and it goes dark. How is the electron feeling?
Well, I thought we were talking about cats here. I mean, the question was one of.
I don't know what would happen to a cat if it went through the two screen and hit. Right. I think it wouldn't feel very good, but what do I know?
Let's just bring somebody else in the discussion. Dink, maybe you have some clarification to make.
Yeah.
If that's okay with you, Jim.
Yeah, I'm okay. Right. I'm sorry. The question was, you said do a calculation, I think. I think that would be a good idea.
No. I said let's bring somebody else in the discussion. I was giving the I was asking Gia this question.
I'll just make a comment that there's a similar thing that we know well about perception. There's a binocular rivalry that has been studied for decades in cognitive science and psychology. You pose two different pictures to your two eyes, what you see. Will you see them in superposition, or will you see one after another? And this is the kind of thing that science could study. Maybe physics cannot study yet, but science could study. Just a short comment.
Okay. Carlo, do you want to?
Jim, I think that Marco and Ding are asking us a technical question here, and maybe I think you should try to give an answer to that. And the technical question. I mean, let me say that you presented your talk. How does it feel to be in a superposition? So then you cannot escape by saying, well, what do I know? What it means to feel. I mean, you presented a precise question. So let me ask a question. Do these two histories decohere? the two histories being the cat, the camera, whatever system you want, passes by one of the two slits, okay, and feel like I feel now of being in a superposition. I don't feel of being in this. I see one particular position of me, some wall, some a precise, and then an interference pattern form. That's history 1, and history 2. The cat passes through the other slits and have a perception of being in that slit, is through that slit, and then being a interference pattern. It seems to me that what Marco is pointing out and what Ding is saying is that in your formalism, these two histories do not decohere. If you do, you would expect of doing this calculation and not decohere. So there is not sufficiently orthogonal in the sense that you refer to, and therefore the coherent history theory cannot predict that if it's included in the history that there is an interference, also there is a specific fact of the matter with a probability associated to it that the cat feels of going up, going through, passes one slit to the other. Am I wrong?
Well, again, I'm sort of nonplussed by. So, do I understand correctly? You're talking about sending a cat through two slits, which you could do, I believe, in principle. And then
I'm talking about the experiment you were talking about, just the kind of things you were talking about, all things which were on your slides.
Right. Which one or what?
Well, let's say the cat that goes through the.
If it's an electron, it interferes, right?
Yeah.
That's the end, and there's a position, right? Coarse-grained, of course, because it's in the plate. Now, we're okay on that?
Yeah.
Okay, it's decohered. If there's a gas outside, and I did this calculation, although I didn't present it on the slide, if there's a gas in the vicinity of the slits, then, first of all, you will be able to detect which slit the electron actually went through from the gas. In fact, this person, Zeilinger, has a beautiful demonstration of that, of just electrons going through two slits, right, with a gas of stuff around them. And you can vary the temperature of the gas.
Yeah.
Okay. So if the temperature is low, right, you get an interference pattern just at the time when the temperature would be high enough that you could tell, right, which slit the electron went through, the interference patterns.
Perfect. So do I understand correctly that when you say we all live in a superposition because we're all in the big, but it follows that we're living in a superposition and we have evidence of some being in one particular history right now. And this evidence implies that we cannot see any interference between other
I think that's right.
Alternative histories. Is that correct?
I believe so, yeah.
Okay, good. Got it.
I hope so.
All right.
It's not a history does not decohere, a set of histories decoheres.
Yeah, sure.
Okay, we can move to.
If I may just shortly interject, this answer is just for all practical purposes. There is decoherence, right? This is not a question of principle. In principle, these histories could interfere, right? So it's not. I mean, I know that I cannot pass through both slits at the same time and interfere with myself. It's ridiculous because I'm too big and we don't have the technology. But as a matter of principle, in principle, according to ordinary quantum mechanics, an object of any size of the universe, could go through a double slit and interfere with itself. So without decohering, right? So decoherence is just for just a technical effect. It's not the fundamental thing that prohibits us from asking the question, what is going to happen in a superposition, right?
No, because the history goes to one slit and then interferes, and the history goes to the other slit and then interferes, do not decohere. So there's no probability associated to them.
Yeah.
There is probability associated to the history goes to one slit, period, and the history goes to the other slit, period. Other things. But if this other thing include an interference effect, there's no probability associated to them. So there's no meaning in associating a probability to them in the current stories.
You might take a look at my little paper. Right? I have a person going through a double slit experiment. In some cases with a gas that would affect decoherence, in some cases not. It's discussed there.
All right, let's move to Igor's question.
I just wanted to ask Jim to please elaborate on that problem of complexity. Where does the complexity in that huge box comes from? Because it seems to me that many worlds interpretation might have a problem with a complexity question. Where does it come from? We see a huge complexity around us, and where does it come from? Just that.
The usual story about animal species or so forth is they evolved from a little piece of DNA over a long period of time. The end result is a complex, very complex structure. That's ordinary classical evolution. So it's possible to get those things without all those histories of that. If we could describe them, the very fact that they would be describable would have to be decoherent. And there are plenty of mechanisms for that. So complexity in the universe starts out in the very early universe, which is remarkably simple, more homogeneous, more isotropic, more nearly in thermal equilibrium. That's on a very coarse-grained scale. We're just looking at the classical properties of it. And there's then classical evolution of all these pieces. But there's also, right, you create environments, right, that allow for quantum fluctuations to grow and make the large-scale structure that we see today. It's a beautiful story. And one of the great virtues of the no-boundary wave function is when you calculate it that way, you get the scale invariant spectrum of fluctuations that we see today. It's consistent with that. In the Planck satellite, for example, it's consistent with the Planck data. Now, to do that, you have to have the correct Hamiltonian, but there is a Hamiltonian from which the data can be fed.
Okay, about that part, but okay, when we speak about complexity, maybe we should clarify. I'm speaking about what is usually called Kolmogorov's complexity or computational complexity. So we can even imagine that we can, in the initial moment, that we have some wave function in that huge box, and that wave function is of some computational complexity, maybe that I can encode it on a CD. And still, after 1 billion of years in this huge box, we can have branches where we have very evolved creatures and so on. And if still nothing has truly decohered and everything is, there is a whole wave function that evolved causally, then the amount of information has not changed. And yet, we see a huge complexity whereas in the start we had everything fitting on one CD. And that is what I see as a problem in many worlds. And I'm not sure what is the general viewpoint over that. If I was
about many worlds, the many worlds experts like Weidman classify decoherent histories as part of many worlds, right? I'm not. I don't have to do anything like that, right? As far as the growth of complexity, the wave function of the universe is fairly simple, as we've taken it, and the early universe is simple. The complexity arises from what are called frozen accidents, chance events that have long-term consequences. One of them was that proton, that ripped through your father and gave you that big nose. It's a chance event that had long-term consequences for you. And biological evolution is all like that. Chance events, recombination, fluctuations, genetic drift, right? So all are probabilistic and give us rise to the complexity which we see today. However, the complexity we see today is only in the middle because of the cosmological constant, right? The universe will get simpler in multiple billions of years because it will expand. It will, the density will go to zero. The stars will die out, right? And according to some theories, the protons will decay. And we will be left again with a very simple universe. So complexity in the universe roughly starts simple, becomes complex because of fluctuations that grow. And then in the light universe, it again becomes simple.
And yet, if the box is isolated and the evolution is unitary, there is nothing that actually happened with the amount of information. It's just unitary evolution. And with a powerful enough computer, I could calculate it. It contains the same amount of information at any moment in the history of the universe.
Well, I'm okay with that. Nothing has changed. It's how much information there is depends on what coarse graining you use to look at it. So, for example, if we just talk about people, we count up people, right? That's a very coarse-grained description of you, right? You're a person. But if we're doing certain calculations, we lump them all together. That's coarse graining. So everything in the universe, quantum and classical, depends on the coarse graining that you use. And there's a choice between them. And you're correct. So there's some coarse grainings that would lead to the evolution which I described. Simple, complex, simple again.
Then there is something that's objectively or not sets this coarse graining, or
beg pardon? Oh, is the coarse graining part of the theory? No, the coarse graining is your choice.
But still we see it. Yeah, I mean it.
Some coarse grainings are better than others, right? And so we like those. Like in biological evolution, we only talk about species, right? Or individuals and so forth. We don't talk about the molecules of the species and try to follow them. We describe the universe at a coarse-grained level. Inevitably.
If I may,
because it's coarse-grained, complexity changes.
If I may interject as well, something might look complicated or complex, but then can also have actually low Kolmogorov complexity. Like, for example, the Mandelbrot set looks awesomely complicated, but you can write a program, 60 lines of code that regenerates all that complexity. So there's no intrinsic contradiction between something that looks complex and something that actually has very low Kolmogorov complexity.
Yeah, there are such examples, but we are pretty sure that what we see around cannot fit on a single CD. Still, there are boundaries to that. And okay, that doesn't prevent us to define Kolmogorov's complexity and so on. But yeah, I agree.
Thermodynamics is another example, right? Very simple laws of thermodynamics. Why do we have them? Because we coarse grain over the molecules and just consider the density to the temperature and so forth. And it's all over the place. It's not surprising. What's simple depends on the way you look at it. Where are we?
We are.
Is anybody interested in my talk? What happened to that?
We're at 1 hour and 15 into discussion. Maybe they're more interested in you, Jim.
Beg pardon? What is it you want from me?
Maybe they're more interested in you, in your own convictions. And I'm sure everybody will read the paper also afterwards. Jim, can you still stay with us a bit more?
Of course.
Yeah, okay. So any more questions or comments?
I like
there are two hands raised.
Oh, I didn't see that.
From Manu and from Ale.
Okay, Ale, can you ask your question?
Yes, thanks for the opportunity. I was trying to think about the double slit experiment in the framework of observers and events to avoid falling in the confusion of cameras and cats and things like that. In this framework, when we are talking about recording, actually we are talking about events of recording, which is a transformation of into a classical information. So I would say that it probably would be impossible to see a recording of something that is still in a superposition of thing, because the act itself of recording is an event, and in this sense is not compatible with the coherence of the object, of the observer that basically is being thrown. So maybe we can see the status of coherence from the launch of the observer, whatever is the observer, to the event of hitting the screen, which is another event actually for the observer, as the only two relevant point in his histories, basically, and so in his experience, given an interpretation of experience as a succession of events, basically, and so say that in the middle it's not well defined, the question of how does it feel, because there are no events in the middle, events of the coherence, and definitely possibly it's hard to define an experience in this sense. It's like the observer is in the flow. I don't know how to explain, but between two events, which is the emission and then hitting the string, as long as he is in coherence, there is no really experience or recording. Could this be a possible interpretation? I mean, the framework of observer and event could help understanding the feeling question.
But that is why we use cats and people in the experiment, because if you are the one being thrown through the experiment, through a double slit, you cannot say that the only experience that you will have is before and after. There is the middle in between, during flight. You have some experiences during flight, so you have to account for those. Or at least you would expect that you would have some experiences if you were thrown into that apparatus, right? Because you do not perceive any gap in your consciousness or something like that while you are awake.
But
so I don't think that it is a good answer to just say that there is no matter of fact of what happens in between. There should be. That is the question we are discussing.
Okay, but the fact that all these classical objects feel something eventually are related to events in the middle, in the flight, basically.
Let's leave Jim comment if he wants to.
Sure.
Well, I'm confused about the question is.
No, I was just trying to.
What is the issue? Could somebody say it again, right?
I'll try to be short. My question was that if we can think about this double slit experiment in the framework of observers and events, if during the flight there are no events, actually maybe it's not right to talk about experience or recording of experience.
Well, I don't know. If we had a big screen with 2 slits on it, right, I would think there would be experience going through it. Just because the slits are so big, they'll let us through.
Yeah, it still would be events of decoherence probably in this context.
Yeah, well, there'd be decoherence, presumably that you would have an environment that decohered the 2 histories, right? Of which we've got plenty, photons.
Thanks.
Thank you.
Yeah,
sorry, Jim.
Yeah, go ahead.
Okay, Manu, can you ask your question, please?
Yes, I just wanted to understand the changeability of past that you mentioned about earlier. We means like you say that there is the future events are probabilistic. Similarly, we could have the past to be probabilistic. But just having a probabilistic past does not mean that the past is changeable, right?
What is the past? There are many pasts.
Yeah, any past that.
Many pasts, many different pasts possible.
So, yeah. So my question is like when we say that we are living in a superposition, and you said that there are several branches, but the experience would come from say only one branch. One branch is what we are experiencing. So similarly, when we say the past is probabilistic, what means what do we mean that the past is changeable? Means I don't see the implication from being probabilistic to be changeable.
We have what we know.
It's the opposite way around. Sorry.
We know about the past comes from present data. We try to calculate a set of histories that goes into the past. We therefore get probabilities for what could happen in the past, not certainties, right? That include whatever experience we had in the past.
I have certainties about the
So Jim, would you?
So I know I know this disagrees with Lee, right? So that's all right. But that's the. By the way, I wrote a whole paper on the what is it called? Something the complexity of the past or something of the past. Oh, I don't know what it was called, quantum pasts and the utility of history. That's the title. It also addressed the issue of why we're interested in the past. After all, it's over and done with.
If I would like to comment on this. You left a question in your last slide, which was whether the future is probabilistic. Sorry, the future is probabilistic. Is the past permanent and unchangeable? But I see that you already believe that the answer is that it's not fixed, the past.
Right, that's right, not fixed in that sense. There are many different paths.
Sorry?
Many different paths you could calculate.
So as time goes on, would you say that the past at the given time, I don't know, at the galaxy formation, is becoming less and less determined because of quantum mechanical uncertainty? The further the past is from us, the less determined it is. That's what I'm asking.
The past is constructed. And as we get further, we have more data to construct, and the past will change. That happens all the time, right? We thought Trump was great, and then we got some more information, and now we think differently in the past. And that can all be done quantum mechanically, right? So the past was never permanent. I think it was never permanent, even in ordinary circumstances, because we got new data, we changed what we thought went on. And quantum mechanically, that's also the case. Right?
I agree with that.
Different histories. Right? I don't know where this idea that the past was unchanging
came from. Well,
I had a lot of trouble with Dyson on this question, but eventually he gave up. Right? He said, okay, there isn't any past. We do everything by starting from the very beginning of the universe and working forward, only going to the future. When we got everything worked out, then we take the conditional probabilities, assuming something about what happened in the past that we already worked out.
There's a beautiful statement by Freeman at the conference for anyway.
Yeah, read Lee's.
Can I have a last very short comment?
Yes, you can. From my point of view.
Okay. I'm continually amazed at where we disagree and where we agree. And let me emphasize this point about the past. Let me just say the way I understand it, and I think you understand it in a way with a different logic, but you come to the same conclusion that there is no past. The way I understand it is there used to be the Copenhagen interpretation. And in the Copenhagen interpretation, there was a distinction made between what was the quantum world that we described with wave functions in quantum states and the classical world that we described with definite values of positions and momentum, wavelengths, and so forth. And what has been proposed, and it's not our proposal, but it's implicit in these quotes from Heisenberg and Schrödinger and other people, what's being proposed is that distinction in the Copenhagen interpretation, which is always movable, is now put where the distinction between the future and the past is. So that they're proposing, and we're proposing to follow it up, to combine the two notions that were different in the Copenhagen interpretation, which is the notion of the quantum world is combined with the notion of the future, and the notion of the classical world is combined with the notion of the past. And that classical world, as you say, is constructed from the records that we have at present and has no other existence.
I think I'm okay with that. Didn't I say something like that? Maybe I didn't.
I'm continually discovering things that you said that were like things.
They were right, with amazement.
Yeah.
It's symmetric, right? Anyway. As it said someplace, the past is a foreign country. They did things differently there. We finished with this, I hope.
Hartle wants to say something.
If there are no other questions, and we still have a few minutes, at the end of the day, I'm a bit confused. I mean, I thought I had totally understand what Jim says, but at the end of all the discussion, I'm a bit confused. So, Jim raised the question. I mean, how does it feel to be in a superposition? And my first understanding was like, come on, it doesn't feel anything special. You're certainly not spread, and I agree. If you ask the answer, do you feel A or you feel B? The answer is either you feel A or you feel B with a certain probability. And here is a way of you compute probabilities. And so far, totally clean. But then, one can ask a little bit sharper question. How does it, so same question with additional condition that we're asking about a situation in which there was interference in the future. There was a fact in the sense the histories we are considering all agree that there was interference in the future. And now it seems to me that suddenly the previous answer doesn't work anymore. Because what you're saying is that if there's interference in the future, the history don't decohere, so there's no meaning in assigning a probability to I feel A and I feel B, irrespective about what we mean by feeling. So I thought the answer was in one direction, and now suddenly I seem to understand that the answer is the opposite direction. Namely, consistent history theory forbids us to ask questions like, how would you feel the cat by go? Or how would I feel going through the two slits if we know that there was interference in the past? Where am I confused? The first part or the second part, or everything is I said is correct?
Maybe the Stern-Gerlach experiment would help. There you have a setup, right? Particles, it goes through this field, right? And it winds up on the other end, right? And so from the other end, we can tell which of the particles went through, right? That's data. We can take that and try to reconstruct the past, and we would get probabilities that it went one way in the magnetic field or another way in the magnetic field, or stuck to the direction of the magnetic field. Does that help? It's decoherent.
No, because in that case, what is the interference? I mean, what does it mean, the interference? I have.
Well, you would have. I'm not sure whether it's interference, but you would have.
Yeah.
Quantum superposition of states. I don't know. Maybe you wouldn't count that as interference. So you could, take inner products of it.
So you're saying that there's a way of posing the question that allows that is in terms of histories that actually do decohere. That's what you're saying. So it's because this is like saying
there are many.
I don't talk about the pattern of the coherence. I have one position and another position, and I'm just asking the question, what's the probability of being this position and the other position? Is that what you're saying?
I think I'm okay with that. I'm not sure, right? But because I didn't understand it completely.
So your answer is the first. It's always possible to, within the decoherent history formalism, to assign a probability for the particle or the cat, respectively, having gone through one slit or the other.
The particle or the cat.
The particle having been through one slit or the other. It's a meaningful probability.
Only if
in all possible cases, you're going to assign a probability for the particle having gone through one hole or the other hole. That's what you're saying.
I don't think so, right? I mean, so it depends on what data you take.
Jim, aren't you saying here if they're part of a consistent history, then yes, and
yeah,
that's your answer. That's what you did.
If the two things decohere, then you can assign probabilities. And in the Stern-Gerlach experiment, we don't try to do that. We just get the output. Anything else I can confuse people? Whoops, silence.
I don't know if you
Any
want
other questions?
Yeah.
That's all I get for explaining the whole universe?
Jim, it's a great, great, great pleasure to hear you do that time again.
So to hear me?
To hear you explain the universe. There are some people who every year are working on something different. Maybe this is unfair to you, Jim, but you're one of these people who in some sense has one paper that you improve and improve and improve and improve and improve.
I'm doing all sorts of things.
I know, but in this subject.
I'm certainly working in the subject of quantum cosmology, which is which is, and finding a formulation of quantum mechanics, right, that will do that for me, because it's obviously not a formulation of quantum mechanics that deals with the measurements of systems from the outside. They're all on the inside. So I think to a certain extent I've done that, but I'm still writing papers about how that actually works.
Mm-hmm. Anyway, thank you.
You're welcome. And it's great to see you. Right?
Yes, thank you.
Well, great to see you. You know, not looking like you have some major problem, whatever major problems you do have.
Thank you.
I'm not going to ask you how you're doing. Right?
We could
like.
There is still Ding Jia that wants to say something.
Yeah, I just wonder, so Jim, on your last slide, you have the first question. Is there any other possible psi other than the no boundary wave function?
Oh yeah, so,
curious
okay.
Because about your thought on this. Why you put this as a question? Do you have an answer to it, or is it something for us to discover?
There are all sorts of competition. For example, there's Alex Filyenkin's wave function, which is different. And various other people probably have wave functions also. All you need, after all, for a theory of the quantum state is something that satisfies the Wheeler-DeWitt equation, basically, which is one of the constraints of general relativity. So there are lots of solutions, and therefore there are lots of possibilities. Pick one. This one seems to be nice because it reproduces many of the observed features of the universe in terms of the history, the probabilities, the histories it predicts. It's no different from dynamics, right? You have a theory of string theory or some other version of it, a different dynamical theory. Well, you don't know which one it is, so you try each one out, see which one gives you the experimental data. Same here. Different wave functions are constrained because the constraints come from general relativity, right? And they give different predictions. Which one do you think is the one for our universe, not on some theoretical ground, but which one makes the best predictions? It's a classic sort of story. We take a theory, we do the computation, we do the observations, we see which one works the best. And there's, if you want to formalize it, there's Bayesian confirmation theory, right, to do that.
Thank you, Jim. There is a person that has been wanting to ask a question, but haven't seen it. Martino, if you're still with us. No? Martino Trasinelli?
Martino is with us, but he has written in the chat that he cannot talk. So maybe you can read the question that
Sure.
The question and the comment.
Sure, sorry. Right, so the cat, it's a which path detector itself. A blind cat maybe could interfere, but it will never know. So a blind cat would be like an electron or a Zeilinger molecule. What do you think about this interpretation?
A blind cat, was that it? That is a sightless cat?
Yes, so Martina is saying that a sightless cat should behave like an electron, but not a cat that sees, because it has which path information.
Oh, I don't know, right? I mean, I would say they're both governed by the same quantum mechanics, right? So I don't think there's a difference. What they see, what they do, of course, will be different. I think I missed the question somehow.
Sorry, I try to ask the question directly. A cat passing through a slit, he's like the buffer of gas of Zeilinger, the experiment.
It's like the
buffer of gas of Zeilinger experiment. Something is changing. But a blind cat, it doesn't feel anything, it doesn't move anything. It's can assimilate like a molecule where no change of state are there, so it could interfere. Of course, it has a mass, so it will move something, but if it's light enough, if there are no state changing, it could interfere with itself, and it will feel anything passing through slits.
Oh, okay. I don't know what the interference of the cat would.
Okay.
Even though I had that slide.
Maybe I can just add a comment, a small short comment. The fact that whether or not the cat can record information mid-flight does not really matter, because I mean that is the information that we aim to answer, to talk about, but in the end that will not destroy interference, because at the moment of the interference, when it reaches when it interferes with the other branch at the screen, it will forget this information. So this information will be erased from its mind after interference. So you can allow the cat to see where it's going mid-flight if only you establish that it will forget this information at the very end. But the same goes with the gas for Zeilinger. So the argument that the gas is somehow basically recording the information about the trajectory of the electron does make sense, but only but in principle we could arrange the experiment so that the gas also interferes with itself. The gas is also a quantum system, just like the electron. So if both the physical system, that is a combination of the electron and the gas, if they both interfere at the end, they will both forget the which-way information. So it doesn't really, the coherence doesn't really help in this setup. I mean,
sorry, Marco, just a second. We should have made it more precise whether there is a quantum eraser before the screen or not. You're presuming existence.
No, the screen is the quantum eraser. The screen itself is erasing the information. So the fact that the cat interferes with itself at the end means that the cat does not have any information about the which-way information after the moment of interference and beyond. But before the moment of interference, we don't know what the cat has, what the information the cat has.
Okay,
because
so
there are two branches.
The screen contains the quantum eraser part. Okay.
Okay.
It's any physical system. You can do that with any physical system.
I'm sorry.
Okay.
Because this is getting a bit out of hand. So, I mean, I think Jim has made it quite clear that yes, that everything has to say about the cat going through a slit. The talk was about the wave function of the universe. Feel free to continue this discussion afterwards. At this point, I would like to thank our speaker. It's been 1.5 hours. Jim, thank you very, very much. We really, really appreciate it.
Okay, I would like to conclude with a quote from Chairman Mao.
Yes, if you have any, please go ahead.
Let 100 flowers bloom and 100 competing schools of thought contend. Thank you very much.
Thank you, Jim.
Thank you, Jim.
Everybody.
Long live to Chairman Mao.
Thank you, Jim.
Thank you, Carlo.
Thank you.
Bye-bye.
Thank you, everybody. Bye-bye.
Bye.